Nginx is the company behind the popular open-source project trusted by more than 450 million sites. They offer a suite of technologies for developing and delivering modern applications. The Nginx application platform allows enterprises to modernize legacy, monolithic applications as well as deliver new, microservices-based applications. Check out infoq.link/Nginx for more information.
Hello and welcome to the InfoQ Podcast. Today on the InfoQ Podcast, I'm talking to Martin Thompson and discussing one of the fundamental problems of distributed systems, consensus, specifically about how Aeron, a high-throughput, low-latency open-source messaging system, is using the Raft protocol to achieve clustering in an upcoming release. Martin is a Java champion with over 2 decades of experience building complex and high-performance computing systems. He is most recently known for his work on Aeron and SBE, or Simple Binary Encoding. Previously, at LMAX in the UK, he was the co-founder and CTO, where he worked on and created the Disruptor. He blogs at mechanicalsympathy.blogspot.com and can be seen giving training courses on performance and currency at places all over the world. Martin, welcome to the InfoQ Podcast.
Hi, thanks, Wes, for having me.
I really appreciate you taking the time to join us. So let's start off. I mentioned Aeron. I mentioned that it's kind of a high throughput, low latency open source messaging system. Could you talk a bit more about Aeron and why you created another messaging system?
Oh, great question. Having worked on many other messaging systems, getting involved in another one seems like a crazy idea. It was kind of born out of a client talked me into it. And we were having coffee one afternoon and discussing what would the ideal messaging system look like, given how the world is quite different now. We have very different hardware than whenever many of the previous messaging systems were around. We have much higher bandwidth, lower latency networking. We have multi-core systems. We just have a very different layout with many more cores on our computers than we used to have. And we wanted to look at, well, what can we learn from the modern hardware and apply that to do a better thing? So we kind of chatted this around and sort of kicked it about. And in the end, I was saying, yeah, you should do it very differently, almost like flippantly. And the guy who I was working with at the time says, well, would you do it for us? And I didn't really want to, but eventually he convinced me. And one of the means to doing it is I agreed that I would only do it if it would be open source, with the main goal that I shouldn't be involved in another messaging system afterwards if we make it open source.
What was the use case that he needed to solve that kind of pushed him towards a new messaging system?
2 things. Like, this was a company that was working at the most extreme end of performance, so they needed performance, but they were close to having what they needed anyway with some of the commercial products. The big issue they had was transparency. To understanding what's going on in a distributed system is a very difficult thing, or even a concurrent system. So our design goal was to build something that was easy to monitor and understand at runtime as a first-class design goal.
So reading the Git repo on Aeron, because as you mentioned, it's open source and you can go to GitHub to be able to get to the code. It says Aeron is an efficient, reliable UDP, unicast, UDP multicast, and IPC message transport. Could you elaborate on that?
Yeah, so we can go over many different mediums. So when you talk about it being reliable over the different mediums, over things like shared memory, it's relatively easy to be a reliable implementation because data doesn't get lost. It doesn't go awry and take different routes in our systems. But once we go over real networks, packets can arrive out of order from when they were sent. They can be lost. They can get duplicates. We can get all sorts of interesting things happen out of our networks. By reliable, we mean that the stream of messages that have been sent from a source to a given destination will be put back into the order in which they were sent eventually, including detecting any loss and retransmission. Quite similar in many ways to how TCP works, in that it sequences everything, works out if there's any loss, and gets retransmissions as a result. But we went with slightly different design goals. TCP, wonderful protocol designed for wide area networks that are quite lossy. So it has certain design characteristics in that in our data centers, we tend to get very little loss and have much greater bandwidth and lower latency. So Aeron had a different set of design goals to make better use of that. So we took different trade-offs. We went in different directions, but the base transport has got very similar characteristics to TCP in what its reliability guarantees are. It's slightly better than TCP, but I like to just think that just compared to TCP is a good benchmark.
When I think about a messaging platform, I think of something like a backplane like Kafka that's used to communicate with the different parts of a system. But as I hear you talk about it, I hear you talk about kind of lower level TCP, UDP, IPC transports. It seems counterintuitive, or at least for me at the level that I operate at, it seems counterintuitive. Am I off base?
Yeah, they are actually quite different. Like we'll put the tag messaging on something, but really what is the set of features that makes up that messaging product? In many ways, Kafka could run on top of Aeron. Aeron could be the transport for Kafka. Kafka relies on TCP, so it doesn't deal with the reliability of the actual messages on the network. It deals with some of the framing issues that TCP doesn't have. So if you think of Aeron, TCP plus a lot of things. So it's got the ability to frame messages. So TCP is a byte-oriented transport stream, so it'll get you bytes from A to B, but it doesn't know where the beginning and ending of, say, messages are inside there. Aeron does. It's message aware, so it gets you there in those sort of orders. And what we're finding is over time, we're adding more and more features to it. So the line between the likes of Kafka and Aeron is becoming more and more blurred. Kafka is a kind of high-level thing looking at enterprise features. Aeron started off as a low-level transmission medium for transport, and it's evolved up adding features that is now becoming quite rich and similar to some of these other things that started as an enterprise system.
Right. So it's definitely a distributed log as well, right?
Yeah, it's got lots of things in there. So the thing is, it's got no dependencies. So if you take the likes of Kafka or many other systems out there, you're dependent on TCP, you're dependent on Zookeeper, you're dependent on many other different parts of a system. With Aeron, you have no dependencies. You're just running on a basic language and a network stack, and it deals with everything from there. Like if going remote, we only need a UDP transport to run on.
Why, Aaron? Now, I know, for example, if you take a look at your Git repo, it's kind of a who's who of performance people: Todd Montgomery, Richard Wilburton, Nitzan Weikart, Martin Thompson. So it has a real focus on performance. What are some of the numbers and metrics that you get for throughput and latency or low latency with Aeron?
In the various levels of transport in the IPC space, we have some of the best latency and throughput of anything out there, depending on whether you've got contended publications or not. It's possible to get into the high tens of millions of small messages per second running over Aeron over various transports. And when they sort of say take about small messages, it's the really interesting test case. Small messages involve exercising the entire mechanism of the stack because you've got to envelope the messages, you've got to put headers on them, you've got to be able to uniquely identify them, you've got to hand them off at any given level. It's easy to sort of get bandwidth numbers by just pushing relatively small numbers of large messages, but then it's just a byte copying exercise. When it comes to byte copying, we can totally saturate pretty much any transport we run over. So if you're running over 10 gig Ethernet, we can just run that at almost full capacity, no problem at all. Most other commercial products can start to push that at that limit when they're running large messages. Let's make it interesting. Run with something like small 32-byte messages and see if they can get close to maximum bandwidth. They don't even get close. We can do it at kind of large or small messages. It doesn't really matter. And a lot of that is just the algorithms we've chosen right down our stack. Works nicely, whether it's small or as large messages. Also, the algorithms work nicely from a throughput and a latency perspective. In some of the high-end commercial products, you have to decide, are you targeting latency? Are you targeting throughput? You can't have both. We have shown with Aeron that that is a fallacy. We don't have a throughput or a latency mode. We just have its normal operation. And as a result, we get the lowest latencies of any messaging product out there and the highest throughput simultaneously.
Aeron's running on 8 today. Is that correct?
That's correct.
Why is that? Have you ported 9 and 10 yet?
We have had it working on 9 and 10. It works on 8. We didn't target 7 because one of the nice features that came in Java 8 was the ability to get at some intrinsics on x86. Some instructions like lock x add, which allows us to increment the number atomically and get the value that it was before it was incremented as a single instruction. And that also scales very nicely on x86 hardware. We use that as some of the core of our algorithms for appending to our log. As you mentioned before, Aeron is a distributed log. We build a log on one machine, and we have a protocol on the network that allows us to reliably replicate that log to one or more target machines, like to one other machine if it was unicast, so one-to-one, or one-to-many with multicast, and we can cope with those. The ability to append to that log from multiple threads requires access to instructions like lockadd to perform well. Java 8 introduced that. It's an instruction that's been around in x86 for some time, but we were able to get access to it from Java as of Java 8. But particularly, we need to get it in a memory mapped file because we're moving these files to network as we're sending. And to work off heap, we don't have the ability through the normal language now to work with memory ordering semantics and perform the changes that we need to change on those files. So things like unsafe is used. As we've gone to Java 9 and now Java 10, we've got nice features for the normal language now that we're having less and less dependency on unsafe, which is a really nice direction to be heading. We're still missing some features that the language doesn't have, particularly with working with memory map files and direct buffers. So if we need to integrate with the network or disk or with other languages, we're having to do things that are slightly out of the normal trodden path.
One other thing that helps you at least get some of the performance with Aeron is you use binary protocols. And I know that the word protocol is probably incorrectly used here, but could you talk a bit about binary protocols in use with Aeron versus maybe a text-based protocol?
Sure. So on the wire, we have a protocol for communicating between the various endpoints in the system for the exchange of messages. Those messages are encoded in a binary format. It's interesting how people will mix encoding and protocol as terminology. The protocol is the sequence of messages that can flow between the different nodes that have a treatment and etiquette to how they should be ordered. Within those messages, we encode data. And it's the encoding that's interesting. When people talk about binary protocols, they're actually talking about how we encode those messages themselves. We could encode them in text with XML, JSON. In fact, actually, some of the messaging products that have been around a long time do some of that, and some of the new open source messaging systems do encode in text. But text is a very inefficient protocol to encode. So you could say, well, are you doing this only for performance? I find this a really interesting question is why do people use text-based encodings for storing stuff in files and on disk or transmitting on the wire? The reason they do it is a really interesting one. It's all about stuff being easy to understand and being easy to debug. Debugging is a key thing that we all need to do. Now, the interesting thing is humans do not read ASCII. They do not read Unicode very well. They have good tools at the moment that let us read ASCII, read Unicode, and so it's easy to debug. The interesting question is not binary encodings being a problem, because it is actually a binary encoding in ASCII. It's just a specific form of it. It's the tools that are available. So if you, as part of your development process, build the tools to understand what you've got, or you get familiar with tools like, if you're working in the network space, things like Wireshark and the dissectors that come with that. You can write a dissector for your protocol and your encodings. Now this becomes very easy to debug and understand. It's a skill set that is not common in our industry. The ability to edit text files is a very common skill. So I don't see the problem as a problem with the encoding. It's a problem with the skill set and the tooling to what people know how to use. And if you think about it, that dealing with these text-based encodings for the times when you do need to go through the development process and bug fixing, that is not how it's used the rest of the time. Computers don't read text. Computers read binary, and they start operating on that, and we have to convert to and from that into different encodings. Like we'll convert to a 2-complement number. We don't deal with an ASCII number in a computer. We deal with the 2's complement representation that's stored in a word. And so we have to go through that conversion all the time, even though it's not needed in the live system. It's needed for the development process. So fix the real problem. Don't deal with the symptom.
That's interesting. So if we want to drive adoption of binary protocols, we need to drive better tooling and support for using them.
Exactly.
Okay, so I want to shift gears just a bit and move into actually talking about building consensus. So specifically, I believe in an upcoming release of Aeron, you're going to introduce clustering, and you had a talk about it at QCon London just in March, where you talked about cluster consensus when Aeron met Raft. So I thought we'd dive in and talk a bit about that journey with Aeron. So Aeron does not support clustering today, is that right?
Yeah, so it's available in the repo. We are going to put a release out shortly that will have it more supported.
So what kind of the design goals for clustering with Aeron?
So the interesting design goal with this is the type of applications that people want to build. If you're working in the financial space and some of the other more complex modeling spaces, we want to build interesting, complex models of a business domain. And to do that, we ideally want to run in memory. So we've got the richness of there's no impedance mismatch between going from their in-memory representation to our database through an ORM. We want to work on that nice, rich in-memory model. But the downside to a rich in-memory model is what happens if the machine crashes? How do we recover that? And the way we can recover that and deal with it is if that model is built on a number of different nodes so that another node can take over in the event of failure of the primary node or the one you happen to be talking to, we now have a reliable system. And if we can snapshot that to disk, we can do all sorts of other interesting things as well. So how do we build these things and run them across many different nodes and agree that they've all got the right version in memory? That's where we need consensus protocols. You need some sort of agreement that each of the machines have got a realistic version of that model in memory so that in the event of failure, one can go from the primary to the secondary or leader to follower, whatever type of protocol you have in place. The interesting thing is, as you build models, we're living in a world where everything is asynchronous. The one that's rebuilding the model could be further ahead. It could be further behind than the one that's responded to the customer. We need to stay in lockstep of the models between what has been shown to the customer. Like if you place an order into a system and your transaction completes, you want to make sure that that's honored. If a follower has not got that data yet, there's no point responding to the customer. You will not have a reliable system. So you need consensus that you have that data on a number of nodes so that in the event of failure, you can proceed. That then raises the interesting question around if we reach that point, a number of nodes, what do we mean by a number of nodes? Well, we need a sufficient number of nodes that we can resolve any disputes. So they're all got different points of state in time. And for that, we need a majority. So most consensus-based algorithms work around the concept of a majority, because when there's a majority, we can break any deadlocks where we don't have agreement.
We were talking earlier, you mentioned kind of my past experience in the military, and I remember there's a certain protocol that you use when you're over a sound-powered phone. When something is given, you have to repeat it back. And I remember specifically in this talk how you talked about the only way that you can guarantee that something's been received at a node is if it's been repeated back and confirmed. So I found that super interesting, a correlation to making sure something's been received and then repeating back to the master.
That is the simplest form to confirm. Like, so if we go right back to the original work of Claude Shannon, where he was describing basic information theory in the 1940s, he highlighted the fact that we get loss and a message being transmitted, even a message being received, is not a guarantee that it's actually understood and being dealt with. And the simplest means to do that is to have it repeated back. We've advanced beyond that. We don't need to just repeat back anymore. We can do checksums. We can do all sorts of ways of checking the validity of something by using mathematics these days. So we've advanced, but it's still fundamentally the same concept.
So Heidi Howard, in her analysis of the Raft consensus, a technical report said distributed consensus builds reliable systems from unreliable components. For your implementation, you specifically chose Raft. Why Raft?
Excellent question. There's kind of multiple parts to the answer to that. One part is that Raft fits very well with Aeron, and that was actually a deliberate thing in the design, which I'll come back to. But the other thing is so why Raft? Why not Paxos? Why not atomic broadcast? Why not view-stamp replication? Why not virtual synchrony? It's interesting. We go back to the 1980s. We had a lot of simultaneous discovery and then future refinement. Paxos was just about first, but very closely followed by virtual synchrony and view-stamp replication. As we go through those, they all have got some fundamental principles, but the nice step that was taken with Raft is it's understandable. It had a different design goal. It's very similar in many ways to Paxos, but it's more strict. And by being more strict, it has got less potential failure cases and less complexity. Both are based upon the concept of electing a leader to then progress the cluster, and the leader determines what the correct order of any given set of events or what the correct order of a value is. The leader can be elected in Paxos that does not necessarily have the latest view of the world, and then you've got to deal with the complexity of reassembling that view. Raft makes a much greater simplification to this, is that you can only elect a leader who has seen the latest view of the world. So then you don't have to go through that phase of recovery. Makes it much simpler to prove and much easier to understand.
Interesting. So when you say Raft is more understandable, what does that actually mean?
The number of potential states the system can be in is less. So it's easier to fit in your head.
I see. Well, you just talked about leader election. I know we don't have a whiteboard or anything to draw on here, but there's some different states that Raft's in, for example. Can you walk through those and give us an idea of how a leader's elected when a cluster comes up?
Absolutely. So at a very simple level, Raft has got this concept of nodes having one of three roles or three top-level states they can be in. Those roles are follower, candidate, and leader. Whenever all the nodes start up, they all start up automatically in the follower state. And so they don't know who the leader is. Then what they do is, with the basic version of Raft, you set a random timer because there's no coordinations, and many of the more interesting advanced protocols in the distributed system space don't have central control. They do stuff using probability theory and randomness to achieve some nice things. So one of the things that Raft does is you set random timers in a number of the nodes that are going to try to become leader. And that means that they all don't tend to do it at the same time. The first one to have its random timer go off will transition to the candidate stage. At that stage, it will request votes of the other members. If it gets votes from a majority of the number of members, it can then become the leader. And so you followed a very simple election process. The thing is, two random timers could happen at the same time, and you'll get a collision, and you may not get the outcome of a single leader from that election, in which case you just fail it, you restart again, and use the randomness again to avoid the collision.
And then as it continues to operate and one, say, a leader drops out, what is the concept of the heartbeat and timers moving forward beyond after a leader's elected?
So once you have a leader, the leader is sequencing the events that are coming into the system and telling each of the followers what is the latest data and how much of that data can you consume. And the amount of that, so they'll give them more data than they're allowed to consume, but they're only allowed to consume up to the point in which the cluster has reached consensus or has a quorum of members that agree that they all have that data so that you could go forward in the case of a failure at that point. And so they're passing that data on. So that will naturally have a liveness property in the system. You know the leaders there, their leaders are live because they're sending you data. If the system doesn't have data for a given period of time to be replicated, the leader then sends out heartbeats periodically to indicate that it's still there, it's still alive, we just don't have any data to replicate. Whenever you don't have heartbeats or data for a given timeout period, you then have to assume the leader is not responsive and not acting as the leader for the cluster anymore. They may have died, they may have been partitioned off from the network, they may be taking a long GC pause, which is actually the most common case that we lose nodes in a cluster these days. People talk about network partitions. Network partitions happen, but very infrequently. Much more common is GC pauses where something doesn't respond for a long period of time and we get that event in which case the followers then among themselves decide to elect a new leader.
When we're talking about consensus protocols, or particularly Raft and Paxos, we're talking about, in CAP terms, we're talking about a CP system, right?
Yeah, it has to be consistent and it has to be available. And so you have to cope with the fact that persistent tolerance is not something you can tolerate.
Okay, so what you just described, if you've got a cluster, say, of 5, and you have a network partition, and the leader stops sending messages, stops sending heartbeats, and you have this partition between these 2 and these 3, you have a situation where those 2 and those 3 may elect their own leader between those partitions, correct?
There's an interesting question. So if the leader dies, how many is left? You're left with 4. Say you're a partition 2 and 2. You know the number of members in the cluster, so you need to get votes from a majority to be successfully elected. In a cluster of 5, neither of those 2 groups can elect a leader.
Okay. So then what happens in that case?
Your cluster has stopped.
It stopped. Okay. So then if you had 6 or 7, if you had enough to gain a majority, you would have a majority on just one side, I guess. Is that the way that would work?
Yes.
So you would never have a case where you could have 2 leaders. Then one portion of the cluster would have to stop.
Yes. You can never have 2 leaders at one point in time. And you should set up your network configurations so that your likelihood of getting a group that could form majority not isolated from each other so you can continue.
I get it. Is Raft a silver bullet when it comes to consensus? Are there concerns or issues or the things that doesn't quite solve?
So as far as electing leaders and agreeing the order of a log, it does a fairly good job. One thing it doesn't do is say how to do that efficiently, which is a different question. So that can work quite well. There are other protocols out there. Many of them all work. The interesting case is some of them have a bit more flexibility around relaxing certain things for RAIDs. For example, view-stamp replication can weaken the model around the strict ordering, same with virtual synchrony. So you can get increased performance, but you've got to trade off the performance against the consistency.
One of the questions that I wanted to ask was about the Byzantine general problem with clusters. So Byzantine general problem is basically describing what happens when you have rogue clusters or nodes that are not necessarily operating with the best intent. Does Raft address this? Is it addressed? Is it something to worry about and consider? What are your thoughts here?
So if you're going to follow the protocol and every node follows the protocol to what they should do, it copes with the scenarios of a machine expiring for some reason. That's fine. It doesn't deal with 2 kind of very distinct cases. One is bugs. So if you've got a bug in your code, it can't address that. You can maybe detect the fact that it's happened, but it doesn't mean you can progress. The other case is the true Byzantine situation where you've got a rogue actor. So somebody decides to inject messages into your network, pretending that a certain state is happening that isn't. So for example, someone claiming to be the new leader. Just claim to be the leader. And from there, the followers have to assume that leader has been elected. That's part of the normal protocol. But no follower should attempt to become leader without a clear majority. So they've broken the rules, they've broken the protocol particularly. If you were to go down the route of dealing with sort of malicious actors coming into the system, you would have to do things like cryptographically sign voting rights, tracking all the message flows that are correct, and have going down the route where basically cryptography is the answer to solving that, but it has a lot of performance implications by going that route.
So we started off talking about Aeron, and then we moved into consensus protocol. Why are these so good together? What makes them such a natural fit for each other?
If you look at the basic Raft protocol, it's an RPC-based protocol. So it's remote procedure calls expecting synchronous interactions. The synchronous interactions really expand the time period in which things happen, which takes longer for consensus to be reached. It also greatly reduces the throughput of a given system. Aeron is a very asynchronous thing by nature, and we designed the underlying Aeron protocol with the mindset to going towards consensus protocols longer term. Todd and I both have a background in both of these types of protocols, and we've designed it that way so that a lot of things that would have happened sequentially in order, which expands the time and reduces the throughput, we can do in parallel. And we can do a lot of things asynchronously, so we greatly increase the throughput. For example, the archiving to disk happens completely in parallel with tracking the position for consensus, for replaying the existing log up to the commit position by any given service. We designed the whole system so as much of that can happen in parallel as possible. And as a result, our throughput figures are phenomenal. So things like if we benchmark our archiver on its own, it can very comfortably run at over 2 gigabytes per second, not gigabits, gigabytes per second, if you have a sufficient SSD that can cope with that.
Very nice. So I mentioned before, Aeron's at 1.8.2. I think you're about to do a release. What's beyond this clustering release? What's coming up on the roadmap?
So stuff for this year is like first release coming out very, very shortly is static clusters, where all the members are known at the time you start the cluster. So you can start with cluster 3, cluster 5, whatever you would like. Our next step after that is dynamic clusters, whereby members can come and go dynamically to the cluster. So we will reach agreement on there's a new members joined that will change the profile for reaching majority. And it allows us to do things like graceful, later step down, hot upgrades of a live system, those sorts of things. We'll be able to do that sort of stuff. And then cryptography is coming after that, because that's one of the things that of all the messaging systems that are out there, as soon as you encrypt them, they are all very, very slow because they're all falling back to SSL. We're going to go with some native stuff directly on processor that can allow us to run at much higher rates of encrypted messaging.
Wow. Okay, now I have some more questions. Like you just talked about dynamic clusters. So if you have the ability to increase the number of clusters, doesn't that change the math on getting a quorum? If you have a network partition, can't you get 2 leaders then?
So the only time you can agree a change is when you've got a running functional cluster.
Okay.
So the leader is agreeing that, so you now have a change of membership. So going from 3 to 4 is interesting. So you've got to look at, well, what is the consensus of going from 3 to 4? Well, it's still 3 is what you need, because for majority, it's always n divided by 2 plus 1. Then when you go to 5, you're in an interesting place. So you actually don't have a lot more redundancy than you think, or availability, based upon going from 3 to 4. The step happens when you go to 5. So the math is interesting as you start dealing with this. You also see people running 2-node clusters. This has been a very common thing, especially in the finance industry. We want a primary and a secondary of something. The thing is, if you lose one of them, you are now running with no backup, no ability to recover if something goes wrong, which is a kind of crazy world to be in.
Now, you also mentioned cryptography. So you're going to use the hardware, I guess, to gain some of the cryptography benefits?
Yeah, so one of the nice things we've got is we've built this system in 3 primary languages so far. So we have a native implementation that's C and C++. We have got Java and we have C#. The native implementation opens up a load of really interesting opportunities for us. Like we've already seen that on Linux, we can run and we can make use of things like send message, receive message, and get a 50% throughput increase on what we can normally get with Java, because Java just doesn't have the NIO calls that let us get at some of the sort of more current, like we're talking quite a few years maturity now, networking calls that are available on that platform. But we could also get direct access by putting some assembler inside our native code to make use of the on-chip cryptography that's available on a lot of modern processors, which can be significantly faster, and especially dealing with the native buffers that we have to encrypt our traffic prior to transport.
Sounds awesome. Well, Martin, thank you for taking the time to chat with us today on the InfoQ podcast.
Thanks for having me, Wes. Been a pleasure.